Alright guys, we're going to get into the concept of line integrals today. Line is kind of a misleading term here. You could also think of these as curve integrals. Let me show you what the textbook definition of these things are, and then we'll look at a nice visualization so you can see that this isn't that as bad as the symbolic version of it makes it seem. So see, we got some kind of curve in space, and we've got a parametric version of the curve. So if I have some curve, here's some part of the plane. All right, so we're just doing R2 for now. So I got some part of the plane, just a collection of X and Y points, and I've come up with some parametric representation of how to get my X's and how to get my Y's. All right, so this is when t is equal to A, and this is when t is equal to B over here on this end. And this is just all the different values, smooth and continuous in between A and B, our parametric representation, and we can get as many points as we want to in there. So that's all we're saying with this part of this page. It's just we've got just a region where this is C. C is the idea of the path in space or in the plane. All right, and now what am I doing? I'm taking that path and I'm putting points on that path in some type of ordered fashion. So there are again, these are parametric plots. So these are X and Y coordinates that correspond to a specific value of t. So when I plug in the first t, I'm here. When I plug in the next one, I'm here, and so on until I plug in the last one. And they're on this path. We would connect it smoothly, but we're going to use specific points along that path to be the representatives of this idea of an integral. Now, when you did integrals in Calculus 1, you made a partition of the xy plane, and you did something very similar to this. You had your first x, and then your second x, and your third x, and all that good stuff, all the way down to the last x, right? And this gap between here was delta x. Okay? And typically we did it uniform. It didn't have to be uniform. We could have, different values, but it's just this was the gap between these things. And what did you do? You used the height, either on the left end, the right end, or at the midpoint to represent the rectangle underneath that thing. So this is Riemann sums in Calculus 1, and we're about to do a Calculus 3 version because, again, we can leave this xy plane, we can come out this direction, and so we have the path that we are going to use for integration. Doesn't have to be a straight line path left to right. It can be in all these different directions. All right, now this delta s, that's like the idea of delta x before. Delta s is what we use in calculus to represent arc length. So delta s would be the length of one of these segments between any two consecutive points. So if we wanted it to be uniform, then these would all be the same. Like if we wanted our delta x's to be uniform, so we had all the same size rectangles. But you don't have to have the same size rectangles in for Riemann sums in Calculus 1. They could be different sizes. And so we see some of these that have really big gaps and some that have smaller gaps. And that's perfectly fine. Okay, but delta s is just the gap between these things. The gap between the change in arc length rather than the change in x. So what's happening is we are plugging in these points into some surface. All right, we're going to plug them into some surface. So that surface, think of something being above this. We got some shape that's, maybe it peaks right here and it comes down above all these things. And so some of these points will be up much higher, some will be lower, and we'll have this path in the plane that looks something like this. And we could do the exact same thing that we did before. We pick values in here, and we get a rectangular approximation of that area. And then here maybe we get a rectangular approximation of that area, and so on and so on. Oops, that's not very rectangular. But you get the idea. We're approximating these shapes just like we did with Riemann sums. They're just on a different path than before. Now, we would connect these with straight lines, right? We would connect them with straight lines, and it'll look something like that. All right, so let's look at, this is an example, a line integral visual that's on GeoGebra. So what am I doing here? I've got this path in the plane, and it's a parabolic path, okay? And I am able to select how many rectangles am I going to use within this. And what I'm doing here, and this like trapezoid method, I am picking, since I have 2 points, I'm using A and E, and see, n equals 2, if you remember, that's how many rectangles I'm going to use, or trapezoids in this case. So I'm going from A to C, and then C to E in this picture over here. And I'm making 1, 2 trapezoids. And that the area of those 2 trapezoids is my approximation of the area. So I'm taking the height at my starting point, I'm taking the height of the point in the middle of these two, and then I'm taking my height at the end point, and I am coming up with the area of those 2 trapezoids, and that's the area underneath this surface over that path. That's an approximation of it. And then if n increases, from let's do just one at a time. So now instead of 2 trapezoids, now I'm using 3. So if I'm using 3, I have to have, I take 3 steps. So 1, 2, 3. I take 3 steps. So 1, 2, 3. All right, along that path. But again, the thing is, the change in S, the arc length, is the same between these. So from here to here along that parabolic path, from here to here along that parabolic path is the same, and then from here to here. And you can see that my approximation of my area has changed. I'm picking up a little bit more because I have the straight lines that's going below the surface is it's smaller than it was before. Like the error is getting less and less. So I'm getting closer to being able to hit that. And just like with Calculus 1, what happens? We make more and more and more of these things, and we're able to mimic the path better. We're not missing, we're not skipping over points along the path, and we get a much better approximation until it now basically looks exactly like the path itself. We put so many, the number of points down there is so dense, we can't tell that it's not just the total parabola itself. And the limit as n goes to infinity, or delta s goes to 0, and now we become ds, it becomes a definite integral. And so this is the idea. What are we doing now? We are finding the area, not volume, the area, because this is a path that has no it has no width to it. So it's a straight line this way, a straight line on top where the outputs of these points along the path hit the function, and we're connecting them together. So it is area. It's the area of this sheet that connects us from our path down in the xy plane up to the surface. So it's the area of that shape that that results when we do this integration. We get just like calculus 1, we get area. It's just now the path doesn't have to be a straight line path along the x-axis. It can be any path in the xy plane. So there is the definition of the line integral. It's just a sum. It's another integral whose sum is defined by a Riemann sum. It's just, again, delta s. The new thing is partitioned arc length. We are moving along some curve, and the distance we move along that curve is arc length, because it's a bending, twisting path, typically in the plane if we're doing 2D inputs and a 3D scalar function. Or you know, we could do it with higher dimension. It's the same concept, but that's the new thing, is this ds. Now, using arc length makes this difficult, because we would then have to find arc length. And as we've seen, some functions, the arc length is not easy to find. So as we've seen before in this course, the derivative of arc length with respect to time is the magnitude of r prime. So how the path is changing in absolute value, basically. So when we sum these up, remember if we said it was magnitude, then going away versus coming back, we still keep counting, because we're still moving along the curve even though we're coming back, so we don't lose anything. So what does that mean? That means that we can, if we just do a little manipulation, our ds differential can be changed to the dt differential if we just multiply it by the magnitude of the rate of change along our path. And that's what we need to use for the analytical purposes of this, because we can find this typically easier than this arc length differential. All right, let's do a line integral just so you can see. This is not this bad at all. The notation looks intimidating, but the math is pretty straightforward, especially given some of the things that we've done with this parameterization of paths, which is what we have to do a lot for this type of stuff. So we want to come up with a line integral where this is our function. This is the surface that we're dealing with. And the path that we're going to traverse is the upper half of this circle. So the stuff above the x-axis. And we're going to traverse it counterclockwise. So in the direction of typical motion, the unit circle as we defined it, moving off the positive x-axis towards the negative x-axis in that direction. Alright, we know we're going to be smooth and continuous along our path because it's a circle, and we can model this, since the circle radius 1, we can model it with the unit circle, and it is the unit circle, so we can model it with just cosine and sine as our parametric equations. Alright, recall the definition. We need r prime, and then we need the magnitude of r prime. That's what we need as part of our differential to change from ds to dt. So since this is the unit circle, cosine sine, the r prime would be negative sine cosine. And so since that is, again, still on the unit circle, negative sine cosine, the magnitude of this is going to be 1. Negative sine squared is sine squared plus cosine squared is 1. Sine squared plus cosine squared is 1, and then take the square root, and you get 1 still. Okay, remember the magnitude of a vector is the square root of the sum of the squared components. So we get 1 for r prime magnitude. Alright, and now we come up with a parametric representation of the path. We said x was cosine, we said y is sine, so we make those changes. And our integral then becomes, if we do this, we get sine minus cosine times sine squared. 1 is r prime dt. And so this is what we would now integrate from 0 to pi, because again that's the values of our parameter that would give us that upper half of the circle. Alright, part of this integration we can do right away. The antiderivative of sine is negative cosine, so we can plug in pi and 0 into that right away. This part we need to do a u substitution. So u is sine, du is cosine dt, and then we integrate that. and we would get sine cubed over 3. Alright, so here's the minus cosine here. There's the sine cubed over 3 that comes from this, and we're evaluating both of these between pi and 0. Alright, now when you plug in pi into cosine, you're going to get -1, but we got a minus out here, so that'll become a +1. When you plug in pi into the sine function, you get 0, so this is going to go away. So far we have a +1. Alright, when you plug in 0 into cosine, you get 1. This is a negative, so that's a -1, but remember this is the bottom end, so we're subtracting. So we're going to subtract -1, that'll be +1. So +1, when you plug in 0, you get 0. So we'll have 1 plus 1, which is 2, which is our area underneath this curve over that upper half of the unit circle. So visually, what have we just found? Let me show you. I've got our function y minus xy squared plotted in there, and then I've got the curves. Number one, the top one there, A being the unit circle, the upper half of the unit circle in the xy plane, and then B, I have the way the unit circle, the upper half, would hit this surface, along the surface. Okay, so what have we just found? We have found if I connect the black curve in the plane up to the black curve where it hits the surface, we have found the area of that shape all along through there. So there I had to kind of bring it into the slide to draw it in there, but that's what we found. We found the area connecting this straight up from the plane up to where it hits the curve. That area is 2 units.